So in this short video, I just want to remind students about compound growth and how to think about calculating the aspects of it. Right? So imagine we have a growth rate of, say, 1%. Well, we're going to write that, think about that as G. We're actually going to write that as a decimal, so 0.01. Right? So that's our starting point. Now imagine we have an initial year, call it S. Say that's our starting year. And let's say we have T. That's our end point, or end year. We'll do this all in terms of years. Now imagine in the first year we have an amount, say $100. So let's call that AS, A sub S. Right? And then eventually at the end of this period, we're going to have an amount, let's call that A sub T. So what we think about here is a situation. We have an initial amount like $100. We put it in the bank. It accrues interest at a rate like 1%. We want to ask in the future, i.e. something beyond year S, right, where T is greater than S, we have some amount in the bank. We want to think, how much is that? Right? So the simple formula for thinking about that, and this should all be very familiar to everybody, right, is that our final amount is simply going to be equal to the initial amount we start with. Remember that $100, right? We apply that compound growth rate in the first year, but then again and again and again every year. And so at the end of the time, we've compounded that T minus S times if T is greater than S. So if S was 0, our starting point, right, and T was 20 years down the road, then 20 minus 0, so this would be compounded 20 times. Right? So let's do a quick example to think about this. Right? Let's imagine that AS equals 100, I mentioned, and let's say that G equals, in this case, let's do 5% or 0.05. And let's also imagine that T minus S does equal that 20. Right? Then just plugging these things in, right, gives us that AT will equal roughly 265.4, I believe. So again, that's just saying that $100 had a growth rate of 5% applied to it over 20 years. So compounded over 20 years, and at the end of the day, 20 years down the road, we're left with $265.40. Right? But we can reverse this too. If this was the simple formula for thinking about what is a value AS compounded at some growth rate G into the future AT, we can ask ourselves, well, what if we know what the endpoint is, AT, how much we have, and we know, say, what we started with, AS, we can actually back out what the growth rate G is over this period of time, given that we're compounding. We're applying that growth rate year by year by year. Okay? So just thinking about this formula, we're going to rewrite it very small right over here. Right? At the end of the day, we can back out that G equals AT over AS raised to the power 1 over T minus S, and I apologize for being a little small here in the corner, right, minus 1. This is the number 1. Right? So this is the formula we're going to use to think about if we know the final value, say $1,000 in year T, and we started with, say, $100 in year S, what is that growth rate that we back out? So let's do that exact example. Right? Let's imagine that AT equals 1,000, right? AS equals 100, right? And let's do the same one where T minus S equals 20, or 20 years in the future. Okay? So doing that, just plugging into this formula, that's going to give us, in this case, that G equals 0.122 or 12.2%. So notice the difference there. In this case, we ended up with $265, right, applying a growth rate of 5%. In the second case, we ended up with $1,000. That meant a growth rate of 12.2%. This brings up a bigger issue. The fact that small differences in growth rates applied or compounded over a long time can have big differences in how much something accumulates. Right? And this matters for thinking about economic growth in the following sense. If we compare 2 years, 1900 and the year 2000, right? If we say started at GDP per capita levels in 1900 of around $1,000, right? And we applied 2 different growth rates, say first 1%, and then in the second case 2%, right? Over that 100 years, what is the difference in the outcome, what GDP per capita would be in the year 2000, right? So that's 100 years, so the T minus S part is 100. Right? The G is either 0.01 or 0.02, and the AS is 1,000. So where does that leave us in the year 2000 with these 2 different growth rates? Well, in the first case, it's roughly equal to $2,700 at 1%. Right? In the second case, it's roughly equal to $7,200. Again, applying the 2% growth compounded over 100 years. Why is this simple math important? Well, that difference between 1 and 2% is really the difference between sort of economic growth that happened before the modern world, i.e. before we get into what is called modern economic growth, and the 2% is roughly the average under what we call modern economic growth, right? And so literally that change of 1% is sort of the rise of the modern world in terms of economics, in terms of economic growth. Going from a world where growth is pretty slow over a 100-year span, right? It's not 0, but it's slow, right? To a world where growth doesn't seem that much faster, but compounded over a long period of time ends up with income and well-being levels that are much, much higher over 100 years.